So we're going to prove the monotone convergence theorem. So I'll start by stating it, then say what's obvious, and then talk about the strategy for the proof. So the monotone convergence theorem. Oh, we start as usual. We have a measure space X, NCA, and mu. And we have a sequence of functions. We have Fn, which are functions from X to the positive reals, non-negative reals. And this is a set of a sequence of functions over the natural numbers. And we also have another function which is going to be their limit. So we have the function f and the sequence of functions fn. And all of these I assume are measurable. And in addition, I know two things. I start with two conditions. One is that f1 is less than f2, which is less than f3, and so on. And this holds mu almost everywhere. By the definition we've seen in the lecture, this means that I'm cheating a little bit, but I say that if I look at the set of x's such that, let's say, f3 is greater than f4, then the measure of this set is 0. Now, this isn't quite the definition because, as I said in the lecture, this can be a subset of a measurable set. But roughly speaking, this is what I mean. And the second condition is, as we would expect, that the limit when n goes to infinity of fn of x is f of x. And again, this holds mu almost everywhere. Okay, so similarly defining what this means for this condition. So f is the pointwise limit of the sequence of functions fn. And what we want to say in this formulation, no. Yeah. I'm pretty sure it still holds, but and what I wish to say is what we would like to say, that if I take the integral over x, the functions fn d mu, then the limit of this n goes to infinity is the over. Which basically means that I can flip the integral and the limit. If I put the integral inside and the limit inside, and then the limit inside, and then the limit pointwise for every function is the function. Okay. And the way we're going to do it is by proving two inequalities. So I'll start with proving proving one direction of inequality and then follow it by okay. Now, one of the two is pretty easy. Can you see which one it is? The first one, right? Because I said I'm going to do it first. But why is it trivial? First of all, just from the definitions, the conditions that I started with, it's pretty clear that also, in addition to the first condition, also Fn for every n, Fn is less or equal than F, although I didn't write it explicitly. You see it? Pretty immediate. And another thing we know is that because the functions they're all positive and I have condition number one, we also have that the integral of f, so the integral of f1 d mu is less or equal than the integral of f2 d mu, so on.
Almost everyone.
Yeah, almost everyone.
So it's actually not entirely because each of the I that you almost equal, and the countable unit could be that F1 is smaller than F2, except for.
Okay, for the almost everywhere part. Yeah.
Does a counting remaining almost equal sense?
I never thought of it. Okay, so I have for any one of those the inequality, and these are also and okay, this goes on, and also these are smaller than f. So this holds also for the integral. So have that and mu the integral for any n is less or equal than the integral f over the set x. Right, this holds for every n. And if I take the limit on both sides, then, well, I can take the limit on this side here as well, but n does not appear here, so it just stays the same thing. So I have the inequality as I wanted it. Okay. So I'm left with proving the other direction. And for doing so, I need to do a few things. First of all, I would like to be able to, so what we want to say, we remember what was the original claim, we want to say this thing. And in order to do so, we need to apply a few tricks. And basically, what we like to have is a way to translate this still sort of abstract notion of measure of set x to which we try to take limits on to a sequence of numbers. And we feel well with taking limits of numbers. Feel comfortable with numbers. Okay, so generally speaking, if we have, let's say, let's write the function g x, and I want to say that it is larger than something. I have two parts to play with. I can put inside the integral function that is strictly smaller than it, or less or equal. And I can also limit the space I'm integrating over. Okay, so I have two things to play with, and I need to define what are the proper definitions I can use so that I can manipulate those two moving parts so that I'm able to lower bound this limit somehow. Okay? So I'll do it, but I want to explain like what what is my motivation. I need to play with the two parts I'm able to in order to translate this into a sequence of numbers. Okay, I know how to take it. So let's do it carefully. So let's start with the picture. Let's say I have the x-axis here, even though it's not the real numbers, it's just an abstraction. And I have and the function f, let's say, looks like this. Not very know what it is. And I take a step function h, which is a step function which is strictly less than I mean, not necessarily strictly, but less or equal than I'll write it formally in a second. But let's say it looks like this.
I didn't say, but step in a simple function.
Oh yeah, simple function. Yeah. Yeah. No, actually, typically I was wrong. Step is used for I think one of those.
Positive.
I'm not quite sure. Simple function. Let's say it looks like this. And right now I don't assume anything. I say let h be any function of this form that is less than f. And as this was f, I have the sequence of functions f1, f2, f3, etc. looking like, say, so they're also increasing functions. And they will never go above the black line of f. And what I want to do for each such function is think about the regions in which this function is above h. Okay, because I want to lower bound this integral somehow. I cannot immediately translate it to f because f is larger, and I want to use something that's smaller. So I want to look at the areas where, let's say, f3 is larger than this h. So this would be here, this region. And where else? This region here, here, so on. And I'm going to call the set of the union of these, I'm going to call them x3 because it relates to the function f3, but not quite. I'm allowing myself a little more slack by adding a parameter epsilon that will say, well, it's not larger than h, but it's almost larger than h. So what I'll actually do is add, let's use another color, with another addition here. It's not good. Another small addition, sorry, here and here, because here the function f3 is almost as large as h. Okay, maybe this one here is almost good enough, so this area is added as well, and here. This will also be part of x3. Okay, I'll formalize it in a second. Okay, so given never trust the markers. And so given function h that is greater than 0 and less or equal than f, and a value epsilon that's a real value greater than 0, I define the sets xn. Here I just show 3, which is a set of elements such that fn of x, I would want to say greater or equal than h of x. But yeah, I do it like this. Okay. And now what can I use this for? Well, I look at this term, at this equation, first of all, without the limit. I'll apply the limit soon. And what I can clearly say is that the integral over x of fn mu is, well, first, and here I need to be a little careful because this wasn't explicitly defined. I want to decrease this number by limiting the space I'm integrating over. Now this would look a little weird at first, but we need to make sure what do we mean here, because we said we defined this operation when mu is a measure on x. Does it mean that mu is necessarily a measure on a subset of x? This is a little subtle, but in either case I can properly define this integral, but by just thinking of the function being 0 on all the rest of the space. Okay? It's very intuitive to us to do this, as this is a positive function, but we need to recall that this is not our traditional maybe yes, but not the way we're used to writing integrals. Okay, so I reduced the space, and now by the definition of the set xn, I can use this inequality and say that this is greater or equal than the integral on the same space of a lower.
Just actually like
Yeah, okay. Right. Okay. How does this help us? Let's see. Now I want to take the limit on both sides of this equation. So I write the limit n goes to infinity here. And now I write the lim n goes to infinity over here as well. This was an intermediate step. So. And now the only place where n appears is in the space. And this is still, like, I tried to translate this term to something I know how I can work with, but I'm still not quite there, because how do I take the limit where I change the set I'm integrating over? So in order to handle this, I want to break down this expression by the definition of the integral of a simple. Okay, so I'll write this definition down. So what is this integral? What does it mean? If I first write, let's say h equals some m, which I don't know, some values ci times the characteristic functions of sets ai. This would be the ai. This just a general way to write the h. So this integral would be 1 minus epsilon and sum I goes from 1 to m, ci. Now I want to take the measure of, and I need to be careful because I'm not integrating over the whole space, I'm integrating over x. So I take AI, the section with x. Oh. And now at this point, when I apply and now I want to apply the limit here, right? Because the first place where n appears is in this expression. And this is a sequence of numbers. So this is a sum over numbers. I still don't know what these numbers are, but I work easily with sums. I feel comfortable. Okay. But what is the limit of this number? This is still like I reduced one weird limit to another one. I have the limit over sets here to a limit over measurements of sets here. But what I want to notice is that I can remove the n from this expression altogether because of the following. If you first notice that by this definition, as the sequence of functions increases, then for every I, the sets also increase. Okay. Because if for a particular x this condition held, then it will hold for a grid. So if I define y to be the union over all x's, then this limit over here is going. You can think about it like they're growing and growing until some point, maybe these numbers keep changing, but in any case, they probably are. But in any case, this is a valid definition that again we know how to handle. This is the union, and the limit of this value is just mu of AI intersection with 1. Right, because these keep increasing, and at some okay, yeah, I don't know what else to write here, but so this is again a little bit cheating because instead of writing a limit, I write this infinite union over sets.
Also, the hidden two directions that are if you want very easy. The other one you can see the case is not something.
Yeah. Now, why is this good? Because what I want to claim in order to write the integral in a nicer way, what I want to claim is that the measure over the complement of y is going to be 0. So let's think about it. The definition of xn says that I need the function to be greater or equal than 1 minus epsilon. Epsilon is not 0, some fixed constant. I want fn to be larger than h of x up to this multiplicative factor. But as I know that these functions are approaching f and h is less than f, at some point I'll get greater or equal than h of x. Right? So all the x's which are meaningful, which have for which the measure is not 0, I mean, I shouldn't say it about individual elements. I should say it about sets, but for basically the set of elements that does not appear in any xn, its measure is 0.
Why?
Let's look here. So the h can be arbitrary, but it's fixed, and it is always, it will be less than f. The blue lines keep increasing, and at some point they'll get the same point as h, or h up to some constant epsilon.
I can't think of an example where y is not just everything.
That's why.
Oh, you're asking why?
Yeah, why?
Yeah, everything here is mu almost everywhere. So there could be like this, I don't know what to call them.
So those sets you don't.
Yeah, there can be, let's say, subset here, some reason measurable, and here the functions behave. Yeah, it's hard to come up with the examples that don't behave this nicely. Okay, so now I want to write, but now since I defined y using this union over ends, I can write this integral without even writing the limit. Because, oh, let's keep the limit for a minute. So after we broke this down, we can write that this equals, let's keep the limit for a while, limit goes to infinity, integral, no, sorry. Oh no, wait a minute, I keep the limit, but I'll write here an expression that doesn't have n at all. So it's 1 minus epsilon sum I goes from 1 and I y, and the limit does not include because n does not appear here at all, and I can write this as the integral over 1 minus epsilon, the integral over y of h d mu. Right, the same way I broke it down here to the definition, I go back from the definition to the quotation. Okay. So now I was able to do something that's almost what I want. What I wanted is to say that the limit, that's the same limit, is greater or equal than integral over x of f d mu. What I got is integral over y of h d mu. And one step I can immediately already do, which is to write 1 minus epsilon integral over x h d mu. And this is true because of this step that I already deduced. Okay, so the part of x which is not part of y just doesn't contribute anything to the integral. And this is a much more convenient state to be in, because we have taken h to be arbitrary. We didn't assume anything about it. And epsilon is also to our choice. This inequality is true without assuming anything about epsilon. So first of all, as this is true, you know that lim and goes to infinity of f and u greater or equal than 1 minus from a for every epsilon. And this means, as I can take epsilon to 0, this means that limit also holds without the epsilon here. And now what I want to use the fact, I want to use the fact that H is my choice. So I can pick H such that, or that H gets closer and closer and closer to F. And this would tell me that I can replace the inequality here with. Okay, so here I use the fact that it's true for every epsilon, so I can. This is taking epsilon 0. And here I say that we can take H as close F as we want. This means that exactly what we want. Yeah, I take the supermom over for all H's and this concludes. So for me, the hardest part was, I got it broken down, like you can find this proof online in several places, but each place leaves aside one thing that looks obvious to us. But again, you start doubting everything that you look at. So first of all, just the legality of this step I couldn't find anywhere. No one even treats this as a thing to even
just say why it's in the measurable.
Why the set?
Because it's an image of the
Go ahead, I don't know the answer.
image of. I think it's a really good story.
Yeah, so maybe something about submeasures, but
Define that.
yeah, I need to define it.
Yeah.
Define it properly.
Actually, when you do it, that's how you form